Hi, in this video I'm going to go through the week 4 poll for fall of 2024. In this question I have given you 4 columns. I'm asking you to match them essentially with their description. So going through this, I see returns a reordered version of the data that has been sorted. So that is actually sort function. It takes an input data and it sorts it. But the problem is that input data is usually a vector because sorting a data frame is more complicated. Are you sorting it on a particular column? Are you using multiple columns? Sort's not that complicated. Sort, a function, just takes whatever you give it and it tries to put it in the right order if it knows how. The type of the type of data matters. So a character gets sorted differently than a number, gets sorted differently than maybe some symbols, things like that. All right, count how many of each unique value occurred in the data. That is the table function. It tabulates the count of various functions. There is a tabulate function. I like table better. So even though I said that word tabulate, I would use table. It counts how many values occurred. It's great. Returns the data provided with duplicate values removed. That is unique. I did have an interesting question of someone who was asking, does unique return the values that are unique? So like that only occur once within a data set? And no, it's any value that exists will get returned once. So all the values in there returned once, I guess uniquely. It was a good interpretation. It wasn't right, but it was a good interpretation. Provides a vector of positions that could be used to sort the vector argument or arguments provided. That is order. And so like it provides a vector that would sort whatever its arguments were given to it, and it allows for nested sorting. And then that's really valuable because it allows us to then use that to indirectly sort something else based on how the argument, usually extracted from that larger object, would have been sorted. So it's like an indirect way. It allows you to do much more complex sorting than just the sort function would allow. This next one is asking you to kind of match a bunch of properties to these different functions. So grep, grepl, gsub, and then the comparison equals equals. So the big thing is that comparison equals equals is really different from these other 3 in that it will only do whole string matching. Like that's its whole thing. It's going to return true or false. Is there a match between each side? Gsub is grep, or maybe regular expression with substitution. So it allows us to use like complex patterns, match some text, and then replace it with what we're interested in replacing it with. grepl is going to do a similar match, but it's just going to return true and false values on whether or not a match or matches were present at each position. So if I have like a length 10 vector, I run grepl, and any of those positions have at least one match of the pattern inside of them, it will return true or false for each position. grep is going to return the positions that contain, again, at least one match within them. So in this situation, what's returned is potentially, and often likely, shorter than the actual object because it's each position that contained a match, which might be quite short, just on how many matches there were. Okay, so returns a vector of index positions, that's only grep. Returns a logical vector of true and falses, depending on if a match was found, that's both grepl and equals equals. It also returns logic, as all of our comparison functions return logic. Returns a modified version of the x argument. The only one that actually has the x argument and is all that similar to it is really gsub. I think you could make an argument for grepl. This one doesn't have an x argument. This one has an x argument, but it only returns the position. So it's definitely not like a modified version. It can often be a much smaller data set. But gsub is definitely the one that best matches. If you'd said grepl, I'd understand why. I just, in the end, like this data isn't like an actual thing being passed back and forth. These are subsequent analyses. Anyways, finds matches based on just parts of the compared string. So in other words, I gave it away a little bit. It does partial string matching. So grep G sub equals does not only compare parts, it does whole string matching exclusively. Interestingly, all three of these can do whole string matching. They just don't have to, and that's kind of their whole thing. They're able to do much more complicated comparisons using those regular expressions. Finds matches based on only the entirety of the compared values. Kind of a weird way to word it. Really, the key thing is it's whole string matching only. That's probably how I should just word it, but there it is. It's equals only looks at the whole value compared to the other whole value on its other side. And lastly, this last one is asking literally the same thing as this one, because regular expressions are how we do these partial string matches. Now, there are other functions that do partial string matching that don't use regular expressions, but regular expressions are the most common way to do this, and they're one of the more powerful ways as well. So this next one says, select the properties that describe each of the objects. One row of a property won't have anything selected. In total, 7 boxes should be checked. Cool. Nice information, gives you some self-check. Congratulations, Pass Nolan. I thought that was a good idea. I haven't eaten lunch, and it's 5:30 p.m., so just bear with me. It's a little bit of a weird day. All right, we've got the marker vec. This is a character vector. It's got some strings. It looks like chromosome positions, then a position after that. Well, this is for SNP markers, which can be defined by position within the genome. So these are how I often personally describe my SNP positions, chromosome and position. Then I am taking those values, and I'll just, don't want to say that phrase. I will reveal my secret here. This is literally how I often start my personal code files, because I will have stored marker information in this form. I will then open it up, and analyze it by pulling apart those values using a G-sub. So here I am matching the underscore and then extending that off to the right using this combination of dots, which stands for any character, and the asterisk, which modifies the preceding character to be repeated any number of times, so 0 or more specifically. Therefore, any integer of times, if I'm being real pedantic. Anyways, sorry, any positive integer. Wow. All right. So we have this underscore. We're then going to extend. That's going to be the match. So what I'm currently wiggling my cursor in front of is the match. This is where people get confused. I am then going to replace that match with nothing. The challenge is that leaves you not with what you matched, it leaves you with what you did not match because of this replacement technique. So in other words, this results in my chromosome, not my position, my chromosome. The second one is going to kind of do the opposite. It matches any character. Okay, that's an any character. Any number of times, whee, until it finds a underscore. And so it's going to start here, and then it's going to stop here because there's no underscore on the right side of this to match. So this is the only match that it can make. Same thing here. It's then replacing that with nothing, leaving you with just 1, 2, 3, 4, and 5, 4, 3, 2. Now, for both of these, we started as character vectors. We replaced text with other character vectors. Probably the trickiest part of this is they all end up being character vectors because, well, this one obviously was. This one probably is obviously still a character vector. It still has CHR standing for chromosome, not for character, although they do kind of look similar. But then vec2, a little bit confusing, but R doesn't automatically convert any piece of text with just numbers in it into numbers. That it requires it to be stored in a different type of way. We call that type. And so like that doesn't automatically happen. Would you have memorized that? You might have really anticipated, had you been more, if you were more experienced with R, that would be a fairly uncommon, but I could see the argument thinking that it would, but it doesn't. That's the answer, it doesn't. Able to be coerced into a numeric vector using as.numeric without creating knob values. Now that is definitely back 2. And that one you definitely should have been able to answer. No problem. Represents the chromosome and position values, so that was marker 1. Represents just the chromosome values, vec 2, or vec 1, then just the position values, vec 2. And that more comes down to, did you read this? Do you know what a SNP is? Can you maybe extrapolate from these names? Chromosome, you've been seeing CHR for a while now, in my class at least, of CHR standing for chromosomes, pretty common. So chromosome 3, position 1, 2, 3, 4. Done. I think that's near the end. This one, I like this question. I don't know if y'all like this question, but I like this question. This really gets at the heart of why you are bothering to learn really anything in this class. The point of a scientist like me, so a biologist really, someone who honestly works a lot with like molecular tools and does like DNA extractions and is like out in the field and making observations. The reason I ended up learning as much computational skills as I did is because I had really complicated processes that I wanted to implement on my data. Now eventually that translated into me getting good at it and starting to work more in the genomic side of things in general, which kind of required computer analysis. But early on, I just really wanted to do some of my analyses in a replicable fashion. And one of those types of analyses is just cleaning data, be it like student-generated data, survey-generated data, as we're playing with here, or data coming from the field with some typos, with things where some, just accidentally jumped to something, dropped the keyboard, and a bunch of text got in. Data gets dirty in lots of different ways. Data's a little bit harder to really structure than people give it credit for. And so we will often have to go through and clean it. So here I'm demonstrating a really common question that occurs when cleaning survey data, and that humans are complicated. Some humans like blue, some humans like navy blue, some humans like light blue, and you have to end up asking yourself some questions. Do I turn each of those values into blue? Do I turn only some of them into blue? If I am going to consider them, should they be one word? Should they be 2 words? Should there be a hyphen? We do actually have to consider all of this, because if we want to accumulate that data in downstream analyses, we often need them to be identical, or at least or maybe even combined into the same value for a particular analysis. So here I'm demonstrating how really I don't want light space blue, and I certainly don't want capital L space blue. Instead, for R, I want light blue. All one word, all lowercase. Light blue is a thing R knows about. I can plot using the color light blue. I can't plot using this color. And so if I'm wanting to go through and I'm wanting to clean my data, I can do this comparison. So student data, $color equals either blue or light blue or navy blue or civilian. And then I'm using that extraction to then assign it a new value. Really, and the values could change depending on what I wanted. That is a great way for cleaning data. I am testing for the positive presence of something, that for this change to occur, so for the value to be overwritten with lowercase b, l, u, e, it had to be an exact match right here. A partial match wouldn't count. And that's very safe. It means that I don't accidentally overwrite light blue with just blue, because that was apparently the strategy I was taking. But that's not true for grep. Grep is very, very powerful. It allows us to explore data using these partial string matches, looking at just pieces of it. I can look for everything that results in loo. So here, blue, navy blue, light blue, blue and green. Also, all of these, blue with a space, all of these would return a result having searched for loo, which could be great for exploration. But if I then overwrote all of those with blue, well, at least one of these absolutely can't be considered blue. It's blue and green. And that's not the same thing. First of all, that's two different values. So this person should probably just be removed from the data set because they couldn't make up their mind, because working with humans is complicated. But in the end, like, I probably shouldn't be searching with this really, really powerful and kind of vague tool and making big changes, like overriding all of them with any single value. So that's really why I separate into two different strategies: an explorative strategy and more of a cleaning strategy that relies on whole string matching and is very safe. I have a lot of control over. Now, in reality, am I ever using things like gsub to clean my data? Absolutely not. I'm using gsub all the time. But it's usually under much more controlled conditions, and I have to think really hard. And sometimes I still mess up, but I have to think really hard about how my pattern might end up implementing if there's any sort of discrepancy in the data. Honestly, it's a large part of why data cleaning is so important is so that I can do things like use gsub in a somewhat predictable way downstream. Because if I hadn't done any cleaning, like if there was uppercase and lowercase mixed into my data set, which is a very common issue, the gsub might behave unpredictably, and it may break my analysis, or even worse, lead to unexpected and unobserved mistakes. And that is the killer for science is if you ever end up making things up, that's the worst thing. Intentional or not, that sort of error can lead to that. I spent way more time. I told you I like that question. And I think, that's the last question. So let's go through this one. This one, an important question. You should understand what each of these different options do on this text. But just for the record, you should be able to go through these and accurately predict without needing to look at any sort of key or run it in R what these would produce. Just saying that flat out. It's the point of the polls, right? But let's go through them. Here I have chromosome 1 underscore number underscore number. Okay, so the problem that we're going to find is that if we are trying to use some of these expansion tools, the expansion tools may be greedy. If they're greedy, that means that if they're doing something like trying to match here, a greedy could potentially extend it over here. A lazy one is going to tend to stop. And that's going to be one of the big differences that we see down here. But now that we've kind of given you that caveat, hold that in your head. Let's go through the examples. CHR ... underscore and then nothing. Okay, so if I have that CHR ... underscore, that's actually not a match. So this string did not have a match at all to CHR ... underscore. And so nothing ends up getting replaced with nothing. So unchanged for that first pattern. This one would be the same as down here, because this would be CHR ... so any character, and then an underscore. And so if you remove that, it would leave you with just the numbers separated by the underscore. So that one would look good. This next one definitely doesn't work. CHR ... and then underscore, that's not a match. And so that one also remains unchanged. So that's how this one would work. Next one, CHR just ... Okay, so CHR ... works well. CHR ... it left an underscore. So if that gets the match and is replaced with an empty character, it leaves you with everything to the right. And so that's going to have a little underscore here. So that can't be the answer. Finally, this last one, CHR ... replaced with nothing, would end up with just 2, 4, 2, and then underscore. So again, that's not going to be a good match. Okay, CHR ... and then a asterisk. This one's going to be a little bit interesting because after the asterisk is a underscore. And the problem is that with that asterisk being greedy by default, it is going to continue to repeat the previous character of dot as many times as it can, as long as a complete match is still found. So let's try to implement that and you'll see why that's a problem. CHR, any character, any number of times, and yeah, that is a match, but it doesn't stop because that's how asterisk works by default. It doesn't stop. It finds this second match, CHR, any character ending in an underscore, and that is a longer match. And so by default, the asterisk is greedy, and it makes that its match pattern. This then gets replaced with nothing, leaving you with only 11242, which is not what you wanted. That same process gets repeated. CHR, any character, any number of times, and being greedy about it, ending here. CHR, any character, any number of times, ending here. That's why this is not it. Now this is the answer. CHR, any character, any number of times, and then an underscore, but be lazy. And so when it's lazy, it stops. That's the end of the match. It does actually continue to search, and all of these, for the record, have continued to search afterwards, but there's no more CHR. If there was a second CHR, then it would get complicated, and we would need to change the code and maybe even do something different to try and solve it. But for what this is, this works because it stops at that first underscore. And if I repeat that, CHR, any character, any number of times, which includes 2 times, and the characters 2 and 3, and then finding a match at an underscore, and then stopping because that's the match. That is its short match. That is fine. That leaves us with 5454 underscore 1124.2. Finally, this last one, kind of fun, not very realistic. I don't know why this chromosome didn't have any letters on it, or sorry, any numbers on it, but hey, let's talk through it anyways. CHR followed by any character, okay, but there's nothing there, any number of times, including 0, that's why, followed by an underscore. So that is in fact a match. So here that any character any number of times is in fact that 0 number of times, whereas here it was 2 and here it was 1. This time it is that 0, and so that's the match right here. That gets replaced with nothing, leaving you with 1242, blah, blah, blah. Tricky, right? Like I said, you should be able to go through this logic and apply to each one. I guess I could do this last one, CHR1 underscore, the only one with that as a match is this one. This circled region would go away, leaving you with 1234, 1124.2, and then the rest would be unchanged. And that's it. I hope that helped.